Hi everyone. I'd like to start this presentation with a story. It happened last year during the installation of an inspection machine. When lenses are rejected for power, a ticket is usually printed with the inspection values and it is dropped in the job tray. Well, one of the lab supervisors asked us to print a certain value on the ticket. And the goal was to get more information about the origin of the problem. But why? Why wait until rejects increases before taking a corrective action? At A&R, we believe this can be different. We believe that using a proactive production management approach, the drift could be detected before it's too late, before the reject rate increases. And this is what I'm going to talk to you about today. But first, I would like to tell you a bit more about who we are. At Automation and Robotics, we have been providing solutions to the ophthalmic industry for 30 years now. We have partners all over the world, big companies and small ones, many small ones. We have subsidiaries or offices in 5 different countries. In 2008, we released the Dual Lensmapper, which is now recognized by many as the reference inspection units for freeform lenses. And last year, we released an inline mapping inspection machine. It is called the Automapper, and we believe this machine can help any lab manage its production more efficiently. Using the Proactive Production Management Framework, or PPM framework, which is divided into 3 parts. First, using an accurate inspection to assess the design replication. Second, the use of statistical process control techniques to detect the drift in the process as soon as it shows up. And third, using fast troubleshooting techniques based on maps to find the source of the issue as fast as possible. So let's begin with the first part, the accurate inspection. Digital surfacing has been a tremendous breakthrough for the ophthalmic industry by providing the means to surface any individualized design directly on the backside of the lens. A process that we call design replication. The change in the technology is huge and the difference in accuracy is impressive. During my last conference, we have seen that with the advent of the digital surfacing technology, the lab needs to rethink the inspection for at least 3 reasons. First, the process is delicate and requires continuous maintenance. Second, the quality of the final product is expected to be higher. And third, the responsibility for the manufacturing of the progressive surface has been transferred from the blank manufacturer to the lab. It actually moved from mass production to RX. And we've seen that among the available solutions, the mapping inspection is more appropriate for the lab compared to the lens meter, which is not appropriate to assess the design replication, and the XYZ table, which has a high cost in price and maintenance. Note, however, there are 2 generations of mappers. A first generation using a single mapping technology, and a second generation using a dual mapping technology. And we have seen how the dual mapping performs better thanks to its higher accuracy and better resolution. So these mappers provide maps, and basically there are 3 types of maps. A measured map, which is the power of the manufactured lens, a theoretical map, which is the power of the targets, and an error map, which is the difference between the two. So the error map is the error on the power for every point of the lens. And this is what we will be looking at during this talk. So yeah, mind the scale. The values of the error map here are between minus 25 hundredth of a diopter and plus 25 hundredth of a diopter. So these error maps often include typical signature of the process, like the ones that are shown here. The signatures are called error patterns, and they have been classified in collaboration with our partner, IoT. And I would like to show you now several examples. This would be the normal pattern. This is an example of an error map of a very good lens. The color is green, which means that the error is close to zero. And the color is uniform, which means it's close to zero for the whole lens. This is the uniform offset pattern. Here the error on the power is different from zero, but it's roughly the same on the whole lens. This can happen, for example, when there is an error on the true curve of the blanks. This is called the center dot pattern. This one is very common. You can see this important and local error at the center of the surfacing block. And here, the error is higher than 25 hundredth of a diopter. Another common pattern is the ring pattern that you can see here. There might be more than one ring, as the picture you can see, and we'll see later what can be the cause of such a pattern. The spiral pattern is impressive, but less common based on our knowledge. Same for the windmill pattern, which shows a rotational symmetry of order 4. The random pattern shows sort of the randomly distributed error pattern. The horizontal displacement pattern, it shows two errors, two error areas on both sides of the corridor. One is positive and one is negative. And as we will see, this can be the consequence of a misalignment of the laser engraving. The arrow around the block center is somehow an error pattern showing an error in this area. And we will see later the process issues causing some of these errors. And the importance of this error can be objectively quantified using the go-no-go feature of the Dual Lensmapper. It includes different criteria. Each criteria provides an error value and a tolerance, leading to a go or no-go decision. Note that we provide an open solution. So each tolerance is configurable and can be set according to the lab quality standard. We even provide a solution where an external system, like an LDS, can make the evaluation of the lens and send the result back to the Dual Lensmapper where they will be displayed. And since it's not easy to quantify the importance of any error pattern, we have developed a new criteria, which we call the Global Mapping Criteria, or GMC. It works on any error pattern. Its value increases when the importance of the defect gets higher, like we can see here for the ring pattern. And it works great. To reach this performance, we have combined two approaches. One that works well with the variation of value when it's spread all over the map. And another approach that works well when the defect is local. And a combination of the two provides a very robust criteria to quantify the importance of the error pattern. The performance of the GMC have been tested on real-life examples. It was done on 166 measurement results, showing 15 types of error patterns. For each measurement, the importance of the error pattern was evaluated by a human expert using 4 scores. 0 for no error, 1 for small error, 2 for medium error, and 3 for high error. What you can see here is the difference of score between the human expert and the GMC. Almost all the values are equal to 0, which means there is a very good correlation between the GMC and the human perception of the importance of the defect. This powerful tool is part of our new inline dual mapping inspection machine. It's called the Lensmapper and uses the same technology than the Dual Lensmapper standalone. It combines 2 inspection approaches. First, it provides a standard inspection as described by the ISO and ANSI standard. So, even if it's a mapping technology, you get the same fosimeter measurements you are used to, and ISO or ANSI tolerances are applied. This inspection is used for freeform and conventional lenses, and it is accurate within 300 of a diopter. For freeform lenses, we go even further and provide a mapping inspection to make sure that the design was replicated correctly. And it can definitely include the GMC criteria among others. But why using 100% mapping inspection? Well, let me give you 2 reasons. First, you can make sure that no surface defect is shipped to your customers. And this can be done with a fosimeter. Second, it provides a continuous feedback on the freeform process quality. Indeed, the go-no-go values, including the GMC, can be sent to the LMS for each job. And this feedback can be analyzed using statistical process control techniques. First, I would like to explain the principles of the statistical process control. At the first stage, the process is analyzed. Then the goal is to detect when there is any drift in the process, using inspection data and statistical methods. You can see here an example of 2 kinds of drift. The inspection values are distributed like a bell curve, and what you see is the change of bell curve along the time. For the first example, you see a drift in the average, meaning if you take the average of, let's say, 100 products, this average tends to change with time. And the second example shows a drift of the dispersion, meaning the difference from product to product increases with time. In both cases, the goal is to detect when the process becomes out of control. To detect a drift in the process, you can track the GMC values along the time. If the GMC values get higher and higher, it means that your process is drifting. Of course, it is advised to use one chart per production line. Note, however, that common statistical process control techniques are more efficient for a mass production process, but here, each lens is different. Since we wish to provide an even more reactive and accurate drift detection, we have decided to launch a research project on this topic and see what we can do. And when a drift in the process appears, it is important to have troubleshooting techniques to find the source of the problem as fast as possible. And maps can help a lot in this process. The GMC values can be used to identify the most critical lenses. You can then use our web application to view the maps. This application is available on our website for free. These maps often include typical signature of process issues. And these issues are related to 4 steps of the freeform surfacing process, which are blocking, generating, polishing, and laser engraving. I would like to show you now a few examples of process issues. First, let's look at an example of generating issue due to a misalignment of the x-axis of the generator. During the generating process, the lens is rotated very fast, and the surfacing tool will go from the edge to the center of the lens, along the x-axis. If the tool goes beyond the center, it's like it goes twice in the same area. So the tool damages the center by removing too much material. On the contrary, if the tool does not reach the center, then it will leave a peak at the center because it doesn't remove enough material there. Second, let's look at a polishing issue that can happen when the polishing flow is simply too low. The polishing flow keeps the temperature down during the polishing process, and if the flow is not high enough, problems can happen. And third, let's consider an issue at the laser engraving station. If the x-axis is not well calibrated, then the engravings will be shifted. When troubleshooting the maps, the goal is to find the link between the error patterns and the process issues, to finally determine what action step to take. Everyone can build its own experience, and we have many of our customers who have done it quite well. To help its customers speed their learning curve, however, Statistical has launched a project, and it's called the Error Pattern Catalog. Their goal is to establish a systematic link between a process issue and a pattern on the error map. They already did a first study in test environments, and I would like to show you 3 very interesting results. You remember the generating issue due to the x-axis misalignment? Well, it has been shown that it creates a center dot pattern. When the offset is positive, too much material is removed at the center and the power is too low at the center. When the offset is negative, there is not enough material removed at the center and the power is too high, as you can see on those 2 error maps. The action step is then to do an X calibration. It has been shown that a low polishing flow will create ring pattern on polycarbonate. Note that this is not really the case on CR39 or on high indexes. And the action step here is then to fix the issue with the polishing flow, for example, to realign the nozzle. Let's look now at the impact of a misalignment of the laser. When the laser engravings are shifted horizontally, the consequence is a shift of the design regarding the engravings. This shift leads to an error map with two error areas on each side of the corridor, one positive and one negative. The action step is here to recalibrate the laser. As a conclusion, we have seen how the PPM framework can help the lab optimize its production efficiency. An accurate mapping inspection can evidence process defects. These defects can be objectively quantified using the global mapping criteria to make sure that no surface defect is shipped to the customer and to provide continuous feedback on the process quality. This feedback can be analyzed using statistical process control techniques to detect a drift as soon as possible. And when a drift is detected, fast troubleshooting techniques based on maps can be used to solve the issue rapidly. Helping you optimize your production efficiency and deliver the highest quality of lenses is our mission at Automation and Robotics. And I hope you will choose us as your partner.